Okay, let's get started. So it's my pleasure to introduce our speaker today. Chet Hosmer is the founder of Python Forensics, a nonprofit organization focused on collaborative development of open source investigative technologies using Python and other popular scripting languages. He's been researching and developing technology and training surrounding forensics, digital investigations, and steganography for decades. He's made numerous appearances and discusses emerging cyber threats on shows such as NPR, ABC's Primetime, ABC News, Australia, so all around the world. He's a frequent contributor to technical and news stories and publications, including the New York Times, Washington Post, Wired Magazine, and others. He is the author of 7 books. He serves as a visiting professor at Utica College in cybersecurity graduate program, and also is an adjunct professor at Chaplain College, where his research and teaching focus on applied Python and other scripting languages to solve challenging problems in digital investigation and forensics. So with that, I'll turn it over to Chet, and he will discuss forensic identification of fake digital photographs.
Great. Thanks, Jerry. Welcome, everyone. Thank you for having me. My experience with Dr. Spafford goes back a couple of decades, where Dr. Spafford sat on the Science Advisory Board at the Air Force Research Lab, were some of the early projects that I was doing for the lab. He was one of the reviewers of those projects and always provided, really insightful comments and kind of direction to kind of move some of those technologies forward. So today we're going to talk about the forensic identification of fake photos. Obviously, it's a fairly timely topic. I've been working on this particular area for a number of years, and prior to that, I've done a lot of work in steganography, which I'm going to also talk about tonight for you. So just as an introduction, we don't have to go through that. Some of my books, where I'm teaching and what I'm doing. And the focus of my teaching really does surround this concept of data hiding, whether it's steganography or other methods that are used to basically hide, conceal, or use for covert communications. And also, obviously, using Python as a primary language for investigation. But we're going to talk about today is this kind of challenge. Today, the internet and social media contains literally trillions of images. And I'm only going to focus today on images. Most of them are harmless and also quite useful. They communicate knowledge, ideas, new concepts, and new ways of thinking, and of course, pictures of our pets. However, a growing number of those images have been manipulated. And the manipulation of those is in order to deceive us, to change the way we think, the way we act, react, or believe, and certainly can cause harm. At the simplest level, they represent visual fraud. And the question is, the simple question or challenge is, can we, in fact, detect the difference between real and fake? Especially when these images come from social media, because when images are posted to social media, they're already manipulated. They've already been stripped of the metadata. They've already been re-encoded in that environment. So the question is, can we actually use those images? This is kind of more of a general question. Once those images have been manipulated when they were posted to Facebook or Twitter, and you want to use them from a criminal perspective, is it legitimate evidence? It's already been altered. Just kind of a thought. I don't have an answer to that question, but something just to think about. So I want to kind of start by examining a few fakes. Some of these are just kind of funny. Some of these are a little bit more serious. And I kind of want to walk you through a few of those just to kind of give you a sense. And then I'll kind of backtrack a little bit to kind of talk about how this all came about. Obviously, this image is an obvious fake. These two airplanes are exactly the same. They're in the same position, same orientation, but they've been laid on this background in order to be able to look like they were too close together, right? So we can kind of see the landing gear, the position of the plane, all of those things are the same for the two aircraft. But they've been pretty well placed on this background, so you can't really tell that it was fake just by looking at it, just by our knowledge of the image. Something a little bit more fun. This is Dwayne Johnson and Zac Efron. And this particular image was created by Paramount Studios. So this image was actually done by a professional organization. You can kind of see how the waves are splashing up on the guys and whatever. And the question is this one fake or is this one real? I'm going to show you kind of the difference of that in a few minutes. Going back a little bit in history, this was the cover of National Geographic in 1982. So this goes back multiple decades. And they were under great criticism for this particular image for a couple of reasons. Number one, they manipulated the image to move the pyramids a little bit closer together to frame it better. They put the camel riders into the picture, and that's how they actually detected it, because the size of the camel riders in the focus of this was wrong. And they came under great criticism. So one of the issues that we have, there are photographers around the world that are producing photographs that actually end up in the media. And one of the problems the media has is, how do I know if this is real or if this is fake? So can it get serious? This is a particular image that was put out during Hurricane Sandy. And that particular image was manipulated and actually pushed off to news organizations, and a couple of them actually put this on broadcast TV, even though this was a completely fake or fabricated image, in order to create panic. So one of the things you can use these images for is, again, to deceive and create panic within those folks that are looking at the images. You know the old saying that an image is worth 1,000 words, but maybe a video is worth 1,000,000 words. So this concept of being able to create these fakes because it's so easy, and the technology that's doing it is becoming much more sophisticated in how these are being done. Artificial intelligence and machine learning are being used in order to create these, to blend these images together in order so they would hold up. Then there's some ones that are kind of fun, right? This is the kind of thing that we see all the time, basically showing us an alien spacecraft on a background landscape. So we're going to analyze some of these later with one of the pieces of technology that I've been working on for a couple of years. Obviously, this one was one on the cover slide that we had. This one is actually fairly well done, and this was actually put together in multiple pieces. This is not just, obviously this is a fake photo, right? You're not flying an Airbus at 300 miles an hour and taking a selfie, right? So obviously this is a fake photograph, but how they actually put this together is actually quite unique. And when we analyze this one, you'll kind of see the different pieces come alive to basically show how this was actually pieced together. So as we kind of move forward, the images become a little bit more serious. And here's one that, again, is trying to basically portray a specific theme, right? And we want to basically bring this together and actually kind of, Vladimir Putin is whispering into Trump's ear, right? This was kind of an image that was put out that was on social media that kind of made its way around to basically provide an image, a thought process. Again, the political aspects of these are fairly significant. This is Vladimir Putin, giving the thumbs up to Merkel and Trump. And this is another image we're going to take a look at and analyze to see if this particular image was real or fake. Everybody kind of get the sense of what we're looking at here and how these images have potentially an impact on people's lives. So before we dive into the analysis of the image, I want to give you a little bit of background on steganography. How many folks in the room have actually done any study or understand what steganography is or played around? Okay, good. Typically, when I asked that question a long time ago. It was before 9/11. I was standing in World Trade Center number 7, and we were having this discussion about steganography and how Al-Qaeda was using that technology to communicate covertly. And it kind of evolved into a lot of technology that I've been working on for the last 20 years, or a little longer than 20 years now. That's where most of the gray and the beard has come from. So talking about the 20-year anniversary, I founded a company a little over 20 years ago, and we were awarded a contract from the Air Force Research Lab back in August of 1999 to actually develop new algorithms to detect steganography or hidden data within electronic files. And whether that was in images, audio files, video files, or even network protocols, those are the areas that we've been doing research now for over 20 years. So how does that relate to fake photos? And we'll talk about that just a little bit more. So where did steganography come from? The word steganography comes from the Greek roots of steganos for covered or graphy for writing. You put those together, you get covered writing. And this was used by the early Greeks and Persians in several forms to communicate and conceal and carry out warfare. Right? This is how they communicated secretly 2,000 years ago. My favorite story about steganography actually comes from David Kahn's book, The Code Breakers. If you've never seen that book, it's a great book. It's a couple thousand pages, but David was a historian at NSA, and he basically wrote a book about the history of data hiding. And this is the story of Demaratus, who was exiled in Persia. When he was there, he wanted to get a message to Sparta to warn them of a pending attack by the Persians. So he took the writing instrument of the day, which was a wax tablet. Kind of looks like an iPad, right? But he peeled the wax off the tablet and engraved the message in the wood, and then put a clear coat of wax back on top, so you couldn't see the actual message. So it's the physical form of covered writing, right? And so that's where we believe the actual word came from in this particular story of Demaratus. And obviously, he snuck that tablet by the centuries of the day and got the message to Sparta at the time. Here's a question for you, though. Are we any better at it today than we were 2,000 years ago? So if I send you an email message that has a picture attached to it and I've hidden a message inside the photograph, can you detect it? Is it being detected? Is it even being looked for? So can we fool the centuries of today, whether they're firewalls, content filters within our environment today? Can we fool them using the same technique that Demaratus used over 2,000 years ago? And I can guarantee the answer is yes. It's still not a solved problem. Just the technology that we're using is more sophisticated in order to be able to perform the hiding aspect. So the question we always ask in cybersecurity is, what's the vulnerability here? The vulnerability in this particular case turns out to be the human weakness. The human weaknesses that we have here are our inability to be able to distinguish close colors together, those differing shades of colors. Actually, women tend to be better at this because they have more cones in their eye in order to be able to detect that. That's why they're more fashionably sensed than we are. That's why I always wear black, right? So we have this inability to detect differing shades of color, especially if they're in the high energy ranges of color. And so even making slight changes to that, we can't detect it. So just kind of a quick review. RGB images, or true color images like you're seeing on the screen today, basically have three color components: red, green, and blue. Each one of those color components has an intensity value that's associated with it. So the intensity of red, green, and blue gives us 16.7 million colors per pixel. So if you think about that, I can color a pixel just with RGB, and there's other higher forms of encoding than just RGB, but that's the typical one we typically look at. When we look at that, we have 16.7 million colors. What if I make a slight change to that? Can we discern the difference between those? And it kind of brings up the fundamental method that is used in image-based steganography, which is least significant bit modification. So if we take the least significant bit of R, G, and B, of those values, and we change them, the question is, can we see the difference? Can we actually take the difference in that color and see it at the pixel level and see what the difference is? This is kind of the fundamental element of image-based steganography. So back in 1999, I was trying to get my head around this, and I wanted to define a definition for least significant bit steganography. And I wanted to generalize the definition instead of making it specific to images. So I wrote this back in 1999, the hiding of data within a digital carrier by slightly altering an insignificant characteristic of the carrier that does not appear to alter the normal rendering of the data. So this can be applied to audio, can be applied to video, can be applied to images or network protocols. Anything that we can make a slight change to, we can define that as least significant bit steganography. So I always have used the Mona Lisa as an image that I talk about to kind of give you an idea of how we do this within steganography. And I do that for a couple of reasons. One is, it is the worst possible image you could use for steganography. Has anybody in this room not seen this image before? Right? So you have an expectation of what this is going to look like, right? That's number one. Number two, it has very low energy colors. It also has very few colors in the particular image. So therefore, we should be able to see the difference if we make a change to this particular image. So in this particular case, this is two images of the Mona Lisa. The image on the left is the original. The image on the right has a Word document embedded in it. So our ability, even in a low energy image that has very few colors and is an image that you have an expectation what it looks like, in that particular case, you can't really see the difference between these two images, even though it's a poor image to choose in this particular examination. So one of the things that we do is, and it's kind of the basis for fake photo detection, and that's why I'm bringing all this up for you, is that we can render the image differently. So in other words, I can, instead of rendering the image as a normal image, I can render the image and show you the intensity of that image, right? And basically render it that way. I can also render the image as saturation. So I can take a look at the saturation characteristics of the image, and I can display those for you, and we can kind of look at that and see if we see differences between the two images, right? I can also do things like apply the Laplace transform to this to basically give us more information about the image itself. And even in these cases, we're not seeing a lot of difference. If I look at the hue of the image, however, we're starting to see some distortion in the image on the right is from the image on the left. Because as we insert data in this, it actually affects the hue angle of the image itself. Each pixel, you can calculate the hue angle of every pixel in the screen and even compare those to adjacent pixels. So this kind of gives us some, but it's nothing really dramatic. So what if I, instead of taking this approach, what if I instead said, well, what if I actually render the image in the area that the image is being altered? We know the least significant bit of this image is being altered, right? So what if I render this image as a single bit image, the least significant bit, let's say, of red, and I want to actually render it from that perspective for both the original and the fake? Anybody have an idea? First of all, let me ask this question. Do you think that there's information in just that single bit of red for the image of Mona Lisa? So the image on the left, if I'm going to look at that, the original image, is there information in that, enough information in that original LSB of red to give us some definition of the image? Any thoughts? Well, let's take a look. So if you look at the image on the left is the original, and there's some information in that red pixel, least significant red pixel, that gives us kind of at least some definition of the face of the Mona Lisa. But the image on the right is the least significant bit after stego. So in this particular case, we've randomly hid information throughout that image, and we've modified the least significant bit so we can dramatically see this difference, right? So this is one of the things that we learned almost 20 years ago about how to actually detect this. That's just a little bit bigger display of the same issue. So the question then becomes, after we've done this 20 years of work to try to figure out how to detect hidden data, and when we're talking about hidden data, we're talking about data that's spread evenly and randomly across the entire image. That's obviously not what's happening within fake photos. Fake photos, the changes are isolated to specific areas of the image, which is kind of different. So the question is, can we apply at some level what we've learned from the detection of hidden content within images? Can we apply that and maybe use some machine learning in order to be able to detect images that have been altered from a fake photo perspective? So one of the things that we wanted to try to do was combine the concept of using Python and ML with intelligent feature extraction. We've done a lot of intelligent feature extraction over the last 20 years to understand what features of the image matter. So whenever you're building an ML environment, one of the key things is what features am I going to extract, and those features have to mean something. They have to have value in being able to discern the difference between those. So using scikit-learn and Python together, we can train this model in order to be able to identify this. So why would we use Python? So we can use feature selection, we can create matrices, we can plot them and kind of understand how that works. We can select different algorithms and produce a subsequent model. So the concept behind this was, okay, can we build a fake image analysis testing script in Python using ML in order to be able to do that? So the first question is, how do we extract the features that would potentially be meaningful based on everything that we've learned, over the last 20 years or so in stego? So if I took the image of Putin and Trump and Merkel in the thumbs up, and what we would typically do is we would break that image down into specific quadrants. instead of trying to look at the whole image, we're going to break it down so that we can actually perform analysis within a grid. And obviously the grid we're using is much smaller than this, but just to kind of visualize this for you, this is what we're going to do, is break this down into quadrants. And then based on that, we can take a look at a specific quadrant within that particular image and look at individual pixels. That's what the dots and the circles represent there, are individual pixels that we want to identify. But what we want to do is we want to basically analyze pixels that are adjacent and do this throughout the entire image. So take a single pixel that's in the center, basically perform feature extraction of that pixel and all the pixels around it to see if we see anything unusual. And the reason why we would see something unusual is that digital cameras that where most of these photographs arise from do a really good job for us. They basically take analog data and they convert it into digital using an analog to digital converter. But more importantly, after that conversion takes place, what happens is software takes over to basically create the actual image. So we have a process that becomes normalized then. We bring the analog data in, we convert it to digital, and then we basically take that information and use software to normalize it. And this normalization allows us to take better pictures, right? The new iPhone camera has 3 cameras, right? The whole point is wanting us to be able to take better pictures. So that normalization process really helps us in the detection of anomalies, so that we can detect anomalies that wouldn't normally come from that software that would generate that. And even when these images get posted to Facebook and Twitter and Instagram and those social media sites, the modification and re-encoding that those processes do, they do it normalized across the entire image, because they don't want to affect the viewing of the image. They want to basically just erase any information that might be in there, right? So you can't see that. So we do this, and we kind of look at it from both a vertical and a horizontal point of view. So to give you an idea of what we do from this point, there's a whole set of characteristics that we can extract, and then we basically put together a set of pandas, basically panel data tables that we're going to use to basically do a supervised learning of the machine learning algorithm in order to be able to know what good and bad is, right? So what we do in this particular case is we'll take images that we know whether they're real or fake, right? We do feature extraction of those particular images. We actually create panel data or pandas from that, and then we actually train a machine learning algorithm and actually produce a model. The problem is, the first time you do this and you think you know what the solution is, you probably get about 50% accuracy of even the training set. Okay, so you have to go back and do this over and over again to basically determine which of those features actually matter. So this process is very iterative in order to be able to get even the training set to work. So I've got this training set of data. Maybe I got 100 images and I take 80 that I'm going to use to train this. And the first challenge is, okay, can I get the ML algorithm to basically give me the correct answer for those 80? Then I can apply it to the 20 it's never seen before, and how do we do there? So we're shooting for 98, 99% accuracy of the training data, and then the non-training data we're hoping to get 95 to 100% in that particular area. Then we know we have something, okay? So that's what we're trying to do. And once we have that, now we can take other images that weren't in the training set, and we can do feature extraction of those, run them through the model, and produce a result. Does this all make sense? Any questions before I kind of walk you through the actual demonstration of the actual tool we've been working on in order to be able to do this? Any questions before I kind of jump to the, I'm good on time it looks like. Yes, sir.
What was the tool you were using originally when you did the LSB rendering?
Yeah, that's a tool called Stego Analyst. Okay, and that tool is developed by Whetstone Technology, a company that I founded back in 1997. And they still do provide that tool out there. So Whetstone produces that tool and algorithms that will do detection of images that have hidden content, as well as audio files and a bunch of other things. But Stego Analyst is that tool. Good question. Anything else? Okay. See if we can do a transition between the slide deck and the actual demo. Okay, so This is the tool completely written in Python using ML. And what we're going to do is we're going to analyze a few of those images that I basically showed you at the beginning. Okay? And so the way the tool works is pretty simple. You can come up and select whatever. We'll do the pilot selfie first. And the first thing that the tool does is actually try to create a baseline of that entire image. So it doesn't kind of do this blindly. It has to basically determine that. And once it creates the baseline and sets some of the parameters that are going to be executed, we can go ahead and analyze the image and actually take a closer look at the areas of the image that we're finding to be anomalous. Areas that have aberrant data in them that we weren't expecting, again, based on all of the things that I told you. So we colorized this image a little bit to kind of show you the areas of the image that are affected. So when you look at this image real quick, I could probably make this a little bit bigger for you. We're finding these areas of the image that seem to be suspect. Remember, there were multiple pieces of this put together. So obviously the glasses were added, the tie was added, all of this information was added to the image to make it look real, like the actual guy was flying and there was things. Obviously the plane wasn't even flying. So one of the questions I usually get is, why is there distortion or anomalies in the engine, right? Well, the engine's not actually running, but they had to make it look like it was running. So they basically actually created some waves in there that basically create anomalies within the image that weren't in the original photograph that's there. So there's multiple pieces. There's the background, there's the plane, there's the pilot, there's the glasses, there's the tie, there's the movement around the engine that we're detecting with the algorithm that are unusual based on the model that we've actually created. Kind of make sense? All right, let's go take a look at something maybe a little bit more fun. We'll do a fun one first. We'll do Zack of the Rock. And this was, again, an image that was created by Paramount Pictures, so they kind of knew what they were doing when they were putting out this particular photograph to basically promote the movie that they were doing. They wanted to make this look real. And when we actually look at this particular image, we notice a couple things. We can obviously see that they were pasted onto this background. This wasn't something that came with it. And you kind of notice that how we're actually able to detect this. But you also notice the algorithm does a pretty good job where it doesn't detect any anomalies within the original photograph. So if you look at Johnson's tattoo, we're not picking up any anomalies there because it was in the original photograph. Nothing was altered there. What was altered was we have a background and we're basically taking these two individual pictures and we're placing them on the background. Yes?
So can we just call those little ants then, or whatever? It's not, I don't see them completely surrounding the, as a cutout.
Yep, you're right. And the reason that is that in certain parts of this, they've done a better job of blending the actual image that they're placing on the background with the background. So there's algorithms that are being used in order to be able to create this. So in some cases, they're doing a better job of that. And I can turn up the intensity, turn down the intensity based on the parameters to show more. But this is what the algorithm came back to and said, okay, I'm looking at the baseline of the image. Now I'm going to basically run the algorithm against this to collect the features to basically detect those areas that are most anomalous.
So we aren't seeing everything.
That's correct. We're seeing tells. That's a great way to talk about it. Is like, okay, there's something seriously wrong with this image, right? It's not real. There's something incorrect about it, and we're looking at different pieces. And even some parts of this, you could even look at it and say, hey, that's a false positive. That was really part of the original image, but it was based on the photograph that was taken. So in other words, whenever we're doing this, we have to have a human in the loop take a look at this. We can give indications that, hey, this image is bad, but we still need a human to actually look at this and say, yeah, this was something that was actually pieced together. Let's go pull up another one. We'll do, let's do the Trump and Putin one, because this one has a couple interesting artifacts that we weren't expecting when we actually ran this. We had to actually go back and do research and say, why is this occurring? So when we look at this particular image, there's a couple areas that seem really obvious, right, of this particular image. Where the two images were merged together, you can kind of see the area where they were actually pieced together. But what's interesting, if you look at, let's take a look at, let me zoom in just a little bit more for you, and we'll look at Putin's eyes in this particular case. And we were trying to figure out, why is that happening? where did that come from? Why are we getting anomalies there? So we had to do some research to figure out why this was occurring. And we found out that Vladimir Putin wears contacts in order to be able to enhance the color of his eyes. So the algorithm's actually picking up the edges of the contacts that don't blend perfectly with the eye. So this is something that was in the original photograph, but it creates enough of an anomaly that we're able actually to pick it up, not only the other ones. And then if you look at the picture of Donald Trump, he wears caps on his front teeth in order to enhance the appearance of his teeth. We had to do some research on that. Why are those coming up in this particular instance? Okay? So basically, the algorithm can not only detect anomalies created based on the algorithm putting these two images together, but it also can basically detect anomalies that were in the original image that weren't real. Okay? So you see what we're kind of doing here? Take a look at one more, maybe two more. Take a look at the thumbs up image. And I'll analyze this one. This is the Vladimir Putin with the thumbs up, and this one's pretty telling what they actually did in order to put this particular image together, certainly the important aspect of it. If I zoom in on this one a little bit for you, you can kind of tell that that's a fake hand and a fake thumbs up. You probably could have told that if you actually zoomed in on the original image, you could probably tell that. But the algorithm is basically detecting this anomaly between where the thumb, whole hand was actually inserted into the photograph, and we're able to detect the outline of that based on how it was inserted, where we're not seeing that in other aspects of the image. Okay? I'll show you one more. This one takes a little bit longer to generate, only because it's a fairly large PNG image, so this one takes a little bit longer to render. So while this is rendering, any questions so far before we kind of jump into this one, because this one takes a little bit? Yes, sir.
So you kind of already answered this when I was thinking of the question, but so if you put in a regularly, completely unedited picture, you would probably still get a few little blips of stuff on there, probably. Based on, certainly the lens of the camera, any defects that are in the camera lens, any defects that are in how the photograph was taken, whatever, you can do that, but they wouldn't be material, right? The ones that I'm showing you here are absolutely material because they basically show, areas of the image that were obviously altered, where the rest of the image is actually normal. And you can kind of tweak these a little bit. So this one with the UFO puzzled us for a while. We said, okay, we've looked at this image from multiple different dimensions and said, okay, why are we not getting anything here? Why are we not getting the edge of the flying saucer and that kind of stuff? Yes.
It's real.
It's real. Yeah. So bottom line, Occam's razor says, the obvious answer is probably the answer. So the answer is this is real. But what does that mean? It means it means that this was probably a drone of some sort. There was two alternatives we've come up with. One is either a drone, so it was an actual photograph taken of this object within this particular image, right? So nothing was altered. That's one observation. Well, the other observation that we've looked at is that the entire image could be computer generated. So if you look at the way CGI works, you can develop computer generated images that look real. Right? If you've been to the new Lion King movie, right? So, this is just so good these days. Those kinds of images will be able to be detected by the fact that we know they're CGI. So those are the two possible alternatives here. Well, the third alternative is it was a real image in a real image. But so just to kind of give you an idea of how all this works and what we're up against, so the challenge is, so how do I need your help? Why do I need your help? One of the things we need your help with is we need more images, both images that are real and images that are fake. So the greater corpus of the images that we have that can identify the different kinds of fakes that are out there will help us improve the machine, right? So the more we can basically train the algorithm with images that are fake and images that are real, because we're doing this in a supervised learning manner, right? We're not doing unsupervised learning, we're doing supervised learning. The more of those we have, the better the algorithm can improve. And we're kind of seeing some of that improvements over the last 6 months or so in order to be able to do that. So with that, let me pop back really quick to the briefing. I think I only have one more slide. So the ways to get in touch with me, I have obviously a LinkedIn page and I have an Amazon author page. So I encourage you to kind of reach out to me, link in with me. If you have some ideas in this particular area, I'd love to hear from you. If you have images that you want to basically provide, love to see those so we can add them to our corpus from that perspective. But with that, I want to, certainly answer any questions that you have to kind of delve into this a little deeper. We have about 10 minutes, so this is wide open for you guys to ask questions. Yes?
I was wondering, is there only specific types of image modification that this detects? Or is it more like layering an image on top of another image? Or does it also look at stretching and things like that, where like it's almost like a smudge of pixels or things are like pulled in certain directions?
Yeah, most of our work in this area has been in the statistical analysis of the variations between pixels within certain regions of the screen, certain regions of the image. And so those anomalies that we're detecting there, those variations that are unusual. So if you look at a particular quadrant of an image, you're expecting a certain amount of variation within that quadrant. But if you find certain pixels that have adjacencies that fall outside that normal distribution, then that's how we highlight those areas that are there. And there's a whole set of statistics that we use on each individual pixel and the associated adjacent pixels in order to be able to do that based on the quadrant that it's in, right? So those are the kind of characteristics that we're looking at, and also the behavior of the overall image, right, of what is normal for the transition of those statistics throughout the entire image. So it's a basis of those. And it goes back to the feature extraction that I was talking about. And one of the problems with feature extraction is you can overweight. So in other words, if you have features that you're extracting, regardless if it's images or something else, if there are features that you're extracting that, let's say, duplicate a value, then you overweight a particular characteristic. So you have to be very careful. And that's why that diagram that I showed you earlier, that you have to really iterate through the process of the images that you're using for your training set and the images that you're using in order to basically try that out after you've actually trained the model. So it's the identification of that training set based on the features that you're extracting that is so important. And that's why you need more and more images that allow you to tweak those characteristics that you're extracting, and which one and how are you weighting those, within the training of the engine.
Thank you.
Yes.
Yeah, so I know you've been talking mostly about images, but would the same strategy would you be able to use the same strategy with, say, a faked video as well?
Yeah, I mean, one of the big concerns today, right, is deep fakes, right? And Google and Facebook have started to release their own versions of deep fakes that are out there that not only are video, but some of them are actually just audio recordings. And it's a real threat today when you think about it from an operational security point of view. If I can fake your voice, and let's say you're in a position of authority within an organization, and I can fake it so that it sounds like you when you made a phone call to make these changes to the system in order to solve a particular problem. And if it wasn't you, right, if it was somebody acting as you, this is a real serious problem. So not only do we need to apply this kind of analysis and this kind of training, so the same model works. It's just what features do I extract that basically will allow me to determine the difference between real and fake. So it can be applied. Obviously, when you take the transition to movies, right, just take that one simple step. Obviously, movies are just made up of a set of JPEGs, right? So you can extract those individual JPEGs and be able to perform that analysis on the individual images to see if those transitions, not only within a single JPEG, but within sequences of JPEGs to see if they're real and if they've changed. Okay. We've done a little bit of this work with CCTV images, where people have taken images and removed people or cars or information out of those images and put the blank street back in to be able to detect if we can see the changes that were taking place there, and we can. But more work has to be done that could allow us to take this to the next level, which would be for deepfake videos, deepfake audio, in order to be able to address that. So it is the same concept, different feature extraction, different information, different weighting, different process that we have to go through over and over again to get the feature set right.
Yeah,
But
awesome.
yeah, great question.
Thank you.
Anybody else? Yes.
This is more of a clarification rather than a question. So, so each of those small yellowed pixels, which denote the significant difference, would generally mean that there are more least significant bit variations when compared to the permitted, the variation allowed, the statistics set by you.
Yeah, let me go back to this image. So in this particular case, it means that we detected statistical variance between pixels and the adjacent pixels based on several characteristics, that features that we're actually extracting there seem to be out of bounds compared to other adjacencies that we're seeing in the same region. Okay, but the actual statistics that we're using, the features that we're extracting in order to do that, are what allow us to be able to provide that. So those little yellow dots basically indicate areas of anomaly that we're seeing in that particular image. Now, we can give you a go, no-go answer as well based on the significance of the anomalies we're detecting, so we can kind of, set aside this particular image as potentially fake and then have a human use the tool in order to do it. But I wanted to kind of show you what it looked like visually, which tends to be more interesting than just saying yes, fake, not fake. Right? Obviously, when you do this and you're building tools like this, it happened when we were working on Stego for all those years. It was so important to be able to see the difference, right? People wanted, well, let me see the Stego. Well, that's the whole point, right? You're not supposed to be able to see it. But we had to come up with ways to render the images in a way that we could actually show that by enhancing those images, so we can actually show the areas that were anomalous, like I showed you with the Mona Lisa. So yeah, exactly. Any final questions or thoughts? Yes.
One more thought. Have you seen the Adobe's AI prototype to spot face editing and that kind of stuff?
Yes, I have. And it's really an interesting approach that they're taking. A lot of the folks that are taking approaches that differ from what we're doing are actually going out and trying to find the original images or original videos and comparing them. I think that's really hard to basically go out to the internet with trillions of images and basically find images that match in order to be able to determine whether they were real or fake. I want to be able to work with just an image or just a video and basically perform analysis on that particular sample. Like if you think about, I tend to think of things like from a forensic point of view. I've got this sample, is it real or fake? Can I attest to that this is legitimate or not legitimate? Or has it been altered? How much has it been altered? Those are the things that I'm looking for versus trying to compare it to a Beyonce image that was over here that was now used in a product placement for somebody else.
Yeah, because then it applies to a specific case.
Right. Exactly. Exactly. Yep. Okay. Well, thank you for great questions. As I was expecting, there are just some newspapers up here if you want to take those, some background on some of the other research that we're doing. And the gentleman that keeps asking the questions, this is one of my, this is my latest book on using PowerShell and Python together. So stop up and I will give you that. But thank you guys. Thank you.